to it. I'm used to it. Okay, so this is going to finish off this section of the notes, and then we have another set of notes we'll get you next week. But yesterday we did empirical formula, and we talked about if you came out to not a whole number, you have to multiply by an integer. So I do want to go ahead and do, even though I told you to work it on your own, I want to go ahead and do exercise 11, which is in your notes. I don't have it written up here, but it's in your notes. And it's giving you a percentage of phosphorus and oxygen. So we're going to, it tells us we have 43.64% phosphorus and 56.36% oxygen. So assume 100 grams. And when we assume 100 grams, those percentages become our masses, right? Right, Adam? Okay. So then that would be 43.64 grams of phosphorus divided by its molar mass, 30.97, which comes out to be 1.409 moles. And then we do oxygen, 56.36 grams, divided by 16 to 1, 3.522 moles of oxygen. When I divide by the smallest, that is not 2. I'm ahead of myself. Sorry, that's 1. That equals 1. This equals 2.5. So clearly we can't have half an atom. So whatever you do to one, you have to do to both. So because of that, we're going to multiply both of them by 2. So times 2 times 2. So then that is 2, and then that is 5. So our empirical formula is P2O5. And then it gave us a molar mass of something, 283. So N is going to be 283.88 divided by the empirical mass of P2O5, which is 141.94. So that is equal to 2. So then our molecular formula is P4O10. Okay? So that's what you do if it has a decimal. Sometimes when you're calculating this N value, it can do the same thing. It can give you a decimal. Same thing, multiply by an integer to get it to be what it is. Okay? Okay, so that brings us to balancing chemical equations. That should be a very quick refresher for you guys, balancing chemical equations. So exercise 13, it's given us some chromium compounds. So it tells us we have solid, this is where practicing our naming comes in. We have solid ammonium dichromate, okay? And we're decomposing it, and it tells us we are getting CO2, no, Cr2O3 plus nitrogen plus water. So now we balance that. So currently our chromium is balanced, but our nitrogen is balanced. So we really only have to do one thing here. How would I balance that? I need to put something in front of water. What did you say? 4. Oh. That was terrible. In my defense, that was left-handed. And I'm not very good right-handed, much less left-handed of throwing candy. Okay. All right, so y'all remember how to balance equations, right? Pretty straightforward. Just balance them. We'll do one more. We have NH3 reacting with oxygen. Yields H2O plus NO. Okay, here's what I want to tell you. I did not let you do this in pre-AP because it would confuse you, but you can use fractions to balance things if you want to. It's allowed. So I'm going to show you both ways, with a fraction, without a fraction. Okay, so if initially I see this, oh, I told you the 2 right there. I'm copying down and I actually wrote it. So if I put a 2 here and a 3 here, then I would need 5 halves. and you can do that. Okay. Matter of fact, you will have to do fractions when we get to thermodynamics, because when you are, some of these things are defined as only forming 1 mole. When you have a heat enthalpy, it only forms 1 mole, and so sometimes you have to use fractions for your reactants so that you can only make 1 mole. So get used to seeing fractions. In this case, how could I get rid of the fraction? Double everything. So this would also be correct. Incidentally, if you did this either way on an AP exam, they both would be correct because they are technically correct. So last year I had a student who in pre-AP whose dad or somebody, I think it was her dad, was either a chemist or chemical engineer or whatever, and was helping them with the balancing equations. And she argued with her dad that you could not use fractions. You know, she argued, and she came and she was wanting me to say, "Oh, your dad's wrong" or whatever. I'm like, he's right. You can use fractions. I just don't do that in pre-AP because it confuses y'all. So you can do fractions, and then sometimes you will have to do fractions. Okay. And so if you were doing something with oxygen, you would just use a mole ratio of 5/2. Okay. But this makes it easier to do the math if you go ahead and get rid of it. But there are times where you have to use fractions and balancing equations. Okay. Okay, here we go. Stoichiometry. Y'all remember this? Okay. And that is very true. This never goes away. It's built into everything. They just assume you know how to do stoichiometry. Very rarely is it outright a stoichiometry question. It's stoichiometry is built into it, and you have to know how to do it to get to the right answer. Sometimes you'll get to an answer, and you're like, "Why is that the answer?" And I'm like, "Because there were 2 of those," and and you're like, "Oh, I forgot to double it," whatever. Okay. So here we have propane being combusted. So we need to balance that. So let's start with that. How do I balance that?
5O2, 3CO2, 4H2O.
Correct. 5, oops, that's a terrible 5. Let's do that again. 5, 3, and 4. And we have 96 grams of propane. So we're going to do 96.1 grams of propane. What's my next step? Divide by we molar mass it, right? 44.11. And we're trying to find out how much oxygen we need, so we're going to use our, what's that thing called from the balance equation? Mole ratio. Look at us. Who said that? Shannon gets a, here, you're close. I can stand too, so I don't hit anybody. Tyler's like, thank goodness I'm not going to get pegged in the head. Okay, so the mole ratio would be 1 mole of C3H8 and 5 moles of oxygen. And now I'm going to use the molar mass of oxygen. What am I going to use for the molar mass of oxygen? 32. It's a diatomic molecule, so the mass is 32. I'm going to need 3 sig figs in my answer, so I would get 349 grams of oxygen. Don't box the answers. I'm so hot. Yeah. On the AP, it's better to not box your answers because they will search and search for things. But if you have an answer box, they tend to just read that. So, yeah. Okay. Hopefully that rings a bell. Yeah. Yes, ma'am.
So, passing through the mass of oxygen, like you know that it's on the same, it's going to be on the same side as propane?
No, it can be on any side. For stoichiometry, I could ask you now how much CO2 would be made. I could ask you how much water would be made. Exactly the same way.
Okay.
Because this mole ratio step right here is how you get from one thing to the other in the problem. So you can solve for anything in a balanced equation if you know one mass. You know one mass, you can solve for all the other masses. Okay? All right. So that's exercise 15. Let's do that. So I'm going to pause the video and freeze it, and I want you to work exercise 15. So exercise 16 is going to be a work on your own. And then the next one, we're going to start talking about limiting reactant. Also, old school word limiting reagent. But if you recall, the limiting reactant is what limits how much you can make. When you run out, you can't keep making it. And the way we do it is we work the problem twice with both reactants and whatever gave us the smallest one. There are other ways to do that, but this is the most straightforward, and kids seem to not struggle with understanding that. So, but before we do that, remember I told you AP likes particulate diagrams and drawings. They like to ask questions like this. They want you to look at that and determine what would be left when the reaction was over, including the product and any leftover reactant. So what they want you to do is figure that out, draw it in the box, and then you would answer questions based on that, or you'd pick the one. So I want you to do that right now. I want you to look at that. You've got the reaction itself is x plus 2y is yielding xy squared, and based on what we have present in the first box, what would it look like when it went to completion in the second box? So I'm going to pause the video. I'm going to let y'all draw, okay? And hopefully I don't make it erase funny. That is correct. Shannon had it right. So you had basically what you do is you count up what you have. You have 3 of the x's, 8 of the y's, which you're going to run out of first, the x. So you can only make 3 of the product. And then, so 1, 2, 3, 4, 5, 6, you used up 6 of the 8, so you had 2 left over. Okay? And that's a simplified version, but they like to ask questions like that. They like to show you those pictures and you count up and see what's going on. It's a very, yeah, because they want you to understand what's going on the particle level. Okay? Okay, so we're going to work this problem. I'm adding on there because I want you to be able to calculate, and I made you do this in pre-AP. I want you to be able to calculate how much excess reactant is left over in addition to figuring out how much product you can make. So first thing we need to do is balance the equation. So we have NH3 plus copper 2 oxide, making some nitrogen gas, some elemental copper, and some water. And I just started giving you the numbers because I copied down what I have on paper. Okay, so in the problem, they gave us that we had 18.1 grams of this and 90.4 grams of that. You don't have to write that underneath it. It just helps us keep track as we're going through. So we'll start with the first one. 18.1 grams of ammonia. And then 17.04 is the molar mass. Our mole ratio is 2 to 1. 2 moles of ammonia. 1 mole of nitrogen. And then what's the molar mass of nitrogen we're going to use here? 28.02 because it's diatomic. And that gives us 14.9. So now we need to do the other one because we don't know if that's our answer. So now we'll do the copper 2 oxide. Molar mass of that is 79.55. That is a 3 to 1 mole ratio. And 28.02. And that gives us 10.6 grams of N2. So that would be our answer. And then we would say that copper is limiting. And then does anybody recall how we calculate excess reactant? Nope, I can't just subtract the 2. Ultimately, I will subtract in a moment, but I have to do something first.
From 10.6, figure out how much it took to make.
Not from 10.6. Well, you could do it from 10.6. You could. But it's because that's how much product we're making. We're going to go and we're going to start with our limiting reactant and calculate in terms of the other reactant. And does everybody have this written down? Because I don't have enough space. I'm going to erase. Copper is limiting.
Is it copper or is it the copper?
Oh, CuO. Sorry, CuO is limiting. Yeah, it always has to be a reactant.
So
CuO is limiting. I'm sorry. Yes.
So for these ones, the one that's less is always the one that's limited?
Yes, because you'll run out of it, and so you can't keep making the product. So whatever makes the smaller amount is your limiting reactant. So you just go back and say, that's my limiting reactant. Okay? All right, so in order to calculate excess reactant, I'm going to erase this because I have no more room. So say goodbye. So we're going to start with that 90.4 grams of CuO, and we're going to now calculate in terms of the other reactant. So the other reactant is the NH3. So we're going to say 79.55, 1 mole, and then that is a 3:2 ratio. And then what we get is that it would take and use up 12.9 grams used. That's how much is used up. That's not how much is left. So then we take the original amount of 18.1 and subtract 12.9, and that would leave us 5.2 grams of excess reactant. So when we did that reaction, we would have 5.2 grams left over. So if we were drawing little particles, we would draw enough NH3 left over. Yes?
So, you use what, like, how did you know that you're supposed to use the NH3?
Well, how am I supposed to calculate for that?
Like, how did you pick NH3 over, like, the other, like, things in the...
Because there's only 2 reactants in the problem. There's NH3 and there's copper 2 oxide. We know that copper 2 oxide is the limiting reactant. We're going to run out of it.
What if there's more than 2 things?
That's not. They're not going to do that.
Wow, wouldn't you just pick the second to last one?
No, if they gave you 3 reactants and they gave you masses for all of them, you would have to do 3 problems and then calculate how much the other reactants are left over. They're just not going to do that. Just don't.
That's a lot of problems.
Yeah. I mean, they're seeing if you know the concepts. They're really truly not trying to totally trip you up. They want to know, do you know the concepts? Like when we're doing the multiple choice and you can't use a calculator throughout any of the multiple choice for the entire year, you should go into that problem. If you see you're going to have to do some calculations, you should go into that problem expecting the math to be easy. Okay? They choose numbers that make the math easy. You may have to simplify it, like say make 122 125, and then if you had 122 divided by 17, change it to 120 divided by 20, and then ballpark it. Because seriously, you can do that in your head or on at least scratch paper, because the answer choices that they give you are all far apart. They're not giving you like 102, 103, 104, 105. They're given to you far enough apart that if you're ballparking it to get there, you'll be able to pick the answer. Yeah. And if you estimated up to do your math, then pick a number that's slightly lower than what you calculate. If you estimate down to do your math, pick a number that's slightly higher. Okay? Because any math that they expect you to do on paper is pretty straightforward. You expect it to be easy. But people get caught up by trying to do 123 divided by 4.5. Like change it to 5. Do what it takes to make it simple. Okay? So, percent yield. Remember what we calculate when we do a stoichiometry problem is the theoretical yield. Okay? In theory, if everything was perfect and we started with 5 grams of something, we would end up with this. Okay? In the real world, it's not perfect, in case you haven't figured that out. And so we calculate something called percent yield. How close did we get? Okay? The actual yield is what you actually go in the lab and get. Okay? So if I were to go in there and perform this reaction and recover so much, whatever I was recovering, nitrogen, what I actually got when I went in there would be my actual yield. And then I would divide that by the theoretical times 100 is my percent yield. Okay? Most reactions in industry that they're doing to make things do not have a very high yield. To make commercial ammonia is actually a fairly low yield, and it's one of the most common products made and used in the chemical industry. But the process, because it's got to take a lot of pressure and all that, it just doesn't get a very high yield. They're not getting 90%. They would love to get 90%, because that's what they're trying to do is maximize their yield, because if they maximize their yield, what are they also maximizing? Profits, and that's the name of the game. Yeah. All right, so last one in this notes, exercise 19. Methanol is the simplest form of alcohol. It is used as fuel in race cars and a potential replacement for gasoline. So suppose we have 68.5 kilograms of CO is reacted with 8.6 kilograms. Calculate the theoretical yield of methanol. and then it tells you if you have obtained this much, actually produced, what is your percent yield. Okay, so guess what I'm going to do? Pause the video, let you work it, and see if you do it correctly. Okay, so here is what it should look like. Hopefully you got something similar. Someone said boo, does that mean you didn't get that?
No, I said boom. What's that?
Oh, boom, that's better than boo. Yeah, okay, questions?
I got one right.
Yay,
Small victories.
yay. Okay, so it's a limiting reactant because they gave me information about both reactants. So I just calculate to see which gives me the smallest. Whichever is the smallest is my theoretical yield, because I cannot make more than when I run out of this. Okay? Did everybody switch from kilograms to grams? Because that'll throw you off if you don't. Okay? Because you cannot divide a molar mass into kilograms. Got to have the same units, apples to apples. Okay? And then it was just what they gave us in the problem divided by the theoretical we calculated. It's 52.3%. All right, that is the end. Not really.
Not really.
Never goes away.
Never goes away.
It doesn't.
Because we